Today's lesson is going to cover horizontal projectiles. As you study projectiles, one of the main things to remember is that the motions are going to be specific to the type of launched object. So today we're going to talk about ones that are thrown initially in a horizontal direction. Let's look at some definitions. First, a projectile is any object thrown and then under the effects of gravity only. A trajectory is the path of the projectile, so that we can actually take a picture of it. Not really as we know, but as in a time period type of thing. So it would be something like, if you do a projectile like this, one that's launched at an angle, or as we're doing today, we're going to launch it and it's going to start horizontally, like so. The range is the horizontal distance. When we talk about projectiles, we need to talk about their independence of motion. Their independence of motion means that the horizontal and the vertical do not have any relationship to each other, just like when we first started talking about vectors. In the horizontal, the motion is constant, and that means that at every point in time as you go through the path, the horizontal distance will be in equal increments. Vertical, the vertical spacing from a vertical distance, whether dropped or thrown, the vertical distance will be the same. So the distance during drop is the same for launched or dropped. Now I want to draw a picture of this for both of these to help explain that. So when you're talking about vertical and horizontal, what happens is we have an object, let's say, that was thrown sideways off of a ledge. We'll have our ledge here, and then here's the bottom, and we want to calculate what's going to happen to it. So it's going to look like this. It's half of a parabola, and we can talk about whether it's dropped or thrown. This is, again, a very difficult idea of whether it being dropped or thrown, that it's going to hit at the same time, and that the velocities vertically will be the same. I'm going to try my best to draw a picture in a way that will represent it fairly close to the distances. So this is dropped, this is going to be launched, and then here. So if you're looking at, and then if you look at it the other direction, horizontally, these distances, which it doesn't look like I did a great job here, these distances should be the same. I probably should have one more in here, and then it looks like they're fairly even. And perhaps one more right here. So if I put those in, I just need a few more moments in time. Oops, I don't need to do that yet. Okay, so if you look at it horizontally, these distances, if I was a better drawer, would actually be correct. It would be equal increments. If you look vertically, I do need to add some in here. If you look vertically here, and here, and here, and here, they should be the same. Again, my drawing skills lack a bit. So that's what they call independence of motion, and how you can actually see the relationship. It is an awkward thing to think about, that something dropped and something thrown can hit at the same time. We'll do a demo about that next week. Okay, now let's actually talk about the equations. Depending upon who's teaching and who is and what book you use, they do it different ways. When I learned, we did not have anything but the basic kinematic equations at all times. We just used the ones that you learned for vectors. And that's perfectly fine. They work. That's how I learned, and I actually still think of it that way. But for most of us, we want to see the differences. So let's look at the equations for both horizontal and vertical. If you've got your horizontal, so then the ones that are going in the x direction, remember that everything is constant. And so if it's horizontally this way, nothing's changing. So the equation that we're going to be looking at is going to be without acceleration, because there is no acceleration in the horizontal direction. So we've got our x direction, and that's going to be equal to our vxi times our time. So our initial horizontal velocity and our time. But what's also interesting is that the initial horizontal velocity and the final horizontal velocity must be the same. Then next, we look at the vertical. And there are the kinematic equations in the vertical direction. It doesn't really matter what order we do these in. It just seems like we seem to start with this one most commonly. Now, please notice that on these, that we have our direction, which is the x for horizontal, y for vertical, and then we have our other subscript that helps us know if it's an initial or a final situation. So the two subscripts just help you to define the term better. And the acceleration due to gravity is still going to be constant. So we've got this one. We have our we'll just do that one. Y equals VYIT plus 1/2 AT squared. But oftentimes this one, this is the case of horizontally thrown, this is 0, so you actually just have V equals 1/2 AT squared, like so. And then of course we have our VYF squared equals VYI squared plus AY. So instead of saying an X, which is a generic term for distance, displacement, we're going to put Y for vertical. Do we have to do that? No, that's not necessary. But it's handy if we want to really talk about the difference in the two directions. Okay, so here we've got the main equations that we need for the problems. Again, you can change them as you need to as far as the terminologies, and you can look at other books if you don't like this way of doing it. But in general, that's what most books will do, some categories similar to that. Okay, so a couple of things. First, if it's launched horizontally, your initial horizontal velocity is not 0, but your initial vertical velocity is, because there is no vertical velocity initially. You're throwing it sideways, and so you've got a situation where you've got an initial velocity only in the x direction. Then you have unbalanced forces. What does that mean? We haven't done forces yet, but it just means unbalanced just means the things aren't equal on each side of the equation, and so therefore that means that something's going to happen. That something that happens is that the object falls to the earth. The next thing is that the earth is going to pull on the object, so it's going to pull it down, and it's going to pull it while the object is still moving. Now, the other thing that's difficult for students to really understand, and for any of us too, is that once you release it from your hand, there are no forces acting on that object except the force of gravity. So there's nothing pushing it horizontally. There's only something pulling it vertically, and that's why it goes down. And now we're going to do a problem. So the problem that I want to work is one where we say a ball is thrown horizontally. At 4.5 meters per second and lands 3.7 seconds later. Okay, so we don't know anything but that's plenty. Okay, so let's draw a picture. On our picture, we've got our cliff or whatever, and we know we're going to launch our ball. We're going to throw it, and it's going to go like this. So then we know a few things. We know that it starts here with initial horizontal velocity, and that's equal to the 4.5 meters per second. We know that Vyi right here is equal to 0. And we know that the time for the whole thing is our 3.7 seconds. Okay. We also, of course, know acceleration due to gravity is 9.8. This is where I think it's very handy, projectiles, to have 9.8 positive down. Mainly because when we do the projectiles that aren't launched horizontally, we have those negatives that we have to put in, but I think it's simpler to do it this way. So now, the question is first, what's the height of the hill, or where it's, whatever you've got it going. So what is that? So that's in meters. And so that's going to have to be y. Y equals the height. We also are going to look for how far out does it hit, which is x. And we're going to look for our VYF, the final vertical velocity. And we want to know how fast is it actually going. Okay, so how fast is it really going here? Well, it doesn't have just y. It still has x pushing it. So we have to figure out that one. So we're going to do all of those. Okay, so I'm going to erase the top part here so we have a little bit more room. While we're looking at all this, we've got that figured out. So it does not matter which order you solve these in. Technically, solving for x is easiest because we have our two objects that we need in the horizontal. If you look at your equations, you'll notice that because there's no acceleration, there's only one equation for it, and that's our actual average velocity equation that we started with in the very beginning of this year. And so we could do that, but let's go ahead and solve for y first, just because I want to. Doesn't matter. So y, you look at your kinematic equations on which one equation you can use. There's two of them, but the only one that we've got is one with time, because the one that has displacement in it, we don't have that. So we've got y equals VYIT plus 1/2 AT squared. Lovely. That falls out. We're left with y equals 1/2 times 9.8 times the time, 3.7 seconds squared. And this is 4.9 times the 3.7 squared, and you end up with it being 67.1 meters that it fell vertically. Okay. All right, so this would be 9 something, and so that's logically, actually it's a little more like closer to 10 or closer to 4 squared, which would be 16. So anyway, it's and then it's 1/2 up, so that's close. Then we can look for x. So we'll do some mental math just to kind of make sure. X is equal to VXI times t. So in this one, we have our VXI, it's 4.5. We've got our time, which is 3.7. Remember, the time is the same for both. So our time ends up being, our horizontal distance ends up being 16.65 meters. We now know those two things. Once you have those, you can solve for pretty much anything else. So our VYF is going to be the easiest one. There's several we could use. The easiest one is really just doing the VYI plus AT, but of course VYI is 0. So, plus AT. And so that falls out. VYF equals 9.8 times our time of 3.7. Well, that's 10, so it's around 37. It's a little slightly less. It's 36.3. Okay. Then I'm going to have to go up here. We'll just go up this way and do the last one. How fast is it really going? Well, if you drew a picture with my little red color so that we can do that, we actually have a triangle. Aw, it's so nice, isn't it? So we've got an angle here that it drops by. At this point, it has both a horizontal velocity that hasn't changed, and it's got the vertical velocity that we just found on the VYF. So we're not going to find the angle tonight. The question doesn't ask for it, and so I'm not going to worry about it. We'll talk about that at another time. But we'll be doing more problems. But we're going to use Pythagorean theorem here for this one. So VF, the actual final velocity squared, equals VXF squared plus VYF squared. Our VXF, of course, is VXI, which is 4.5. And you don't have to have the parentheses. And then the VYF here is 36.3 squared. The final answer for this one, of just the magnitude of the velocity, is 36.6 meters per second. You notice that it's not very much larger than our 36.3, but 4.5 is not a big value. And of course, this is a very tall cliff to be standing on, and because you notice it's 16.65 meters, and so it's a logical answer. I know it seems a little strange. Okay, hopefully that's enough to get you started. Good luck with doing the worksheet, and I will see you next week. Bye.